Just in case you don't have access to the Canvas inbox where I emailed you the schedule, you can pause the video if you need to jot down any of this or take a screenshot. We are down to our last chapter and a half. If you look ahead, you can see chapter 5 is a little bit long, but chapter 6 we're just doing 3 lessons. Well, 4 if you count that one divided in 2. I'm hoping that you can get about a week ahead at least. That would make things a lot easier. And let's get started with a review of logarithms, and then we'll do some calculus with logarithms, differentiation. So the way I look at logs is, so we have a log, and we have a base, and then this, and then this. They have names, but so when I would see a log, I would think of this to this power equals, and that's how I would convert the equation. So I would say, okay, this to this power equals that. So I would come over here right away, and one of our techniques for dealing with logarithms is to switch it to an exponential. Okay, and another thing we'd like to mention is that the natural log is log with a base e. Now we never write it like this, but that's what it represents basically. Okay, so it is good to know that logs are exponents. Okay, and I guess to rewrite that we could say log base answer exponent. I guess some people have learned it like that. Okay, so we learned about logs in pre-calculus as the inverse of exponentials, and the natural log is e. The natural log is the inverse of e. So, but there's a way to define it with calculus. Now, obviously, you didn't define it using calculus in pre-calculus because you hadn't had it yet. But so what that is saying is 1 over t would be something like this, and it would go like that. Might have been a little bit too steep there. And if we take that from 1 to x, whatever x is going to be, so the natural log of x is equal to the integral from 1 to x of 1 over t. So you don't really need to know that. It's not going to come into play, but that's what it is. The domain is the set. The domain of the natural log is a set of all positive real numbers. If we graph the natural log using a slope field in this differential equation, they're asking us to do that right here. So that's a period. So this is telling us that the initial condition is 1, 0. All right, and that's our differential equation, and that's our that's how we're going to find the slopes of our tangent lines. So this is a nice review of slope fields. So there's no y here. So what that means is it's autonomous in x. That means that, remember, all the slopes will be the same vertically. So we can't plug in 0 because we're not going to divide by 0. So if we try a couple things here, so we call this 1. If we plug 1 in there, we get 1. So I'm going to set that there. And you can fast forward. If you know how to do this, then do the whole thing and then fast forward and compare it. So we said this was autonomous in x. So I'm just going to move up and down the vertically here. So when I plug in 1, it doesn't matter what y is, the slope's always going to be 1. And finally, down here. And that's kind of smudged, but oh well. Alright, so we go over here. The slope is 1/2. So I want to get that smudge action going there, so I'm going to try to just do that myself. So 1/2 would be over here, so that would be about right there. And oops, it's kind of long there. And here and here. Okay. And then if we plug in 3, it's 1/3, so that's even. So that would be over there. So it's just a little bit flatter than that one was. I should have just paused this. I'm going to pause it and finish those. Alright, so I finished those 1/3 slopes, and I plugged in 4 and got 1/4 for the slope here, so that's just a little bit flatter. So we take the initial condition now that we had here, 1, 0, and plug that in here. And remember, if that's the current and we dropped a leaf in the current there, it would go something along these lines over here. And this would kind of go down this way, like that. So that gives us the natural log. Okay. Now, if we, and again, that's not that big of a deal. It's a nice little review of slope fields. It's showing us that the graph of the natural log fits into that slope field, with that being the derivative, where the derivative is equal to that. Now, let's go over properties of exponents real fast. So, and properties of logarithms that kind of go together. So remember, logarithms are exponents. So if I take the natural log of a product, then I'm adding the exponents. Natural logs are exponents. So we're adding the exponents. So that goes back to our rule here. When we multiply two things with the same base, we add the exponents. And that shouldn't be that big of a deal. We shouldn't have to memorize that rule. We can just look at what it is. This is x times x. This is x to the 5th. And that would be 7 x's being multiplied together. So that fits that. Here we would be dividing, and so we would subtract. And here when you have a power to a power, you multiply. Now again, you shouldn't have to worry about am I adding or multiplying. If you think about what this means, it means x cubed times x cubed. And then we would be adding those together. So that would be x to the 6th. Okay. Now, over here, this is just kind of showing us that the natural log of 1 equals 0. And if you think about it, why? It's because e to the 0 equals 1. So that's something we kind of want to have memorized. Okay. So the rest of this page is pre-calculus or algebra 2, both. You should have had it twice, depending on what happened last year. So the property here is you take that out and multiply it. Okay, so we take this out in front and multiply it by the natural log right there. So that's pretty, hopefully you remember these rules or they come back to you fairly quickly, and that's it. Now, This one messes students up sometimes, so let's just do it one step at a time. So we have the natural log of this, and then division, so we subtract. So then we have the natural log of y times z. So what happens here, this is a lot of steps, but what happens is we have here the natural log of y plus the natural log of z. And so what happens here is we have to distribute that. And here's where the mistake comes in. Some students skip this step and they don't think about the negative, and they don't put these parentheses, and so they just have this one as negative, and that would be incorrect. So we want to make sure that we have both of those negatives. So if this is a total review for you, you could pause the video, do all of this, and then forward and see if you did it correctly. Alright, last one over here. We have a couple things going on, so we want to do, that's multiply, so we're going to have the natural log of e plus the natural log. I'm going to do it one step at a time, so that's going to be x squared. So that's going to come over here. Now here, what we want to ask ourselves is e to what power equals e? Right? E to what power equals e? Well, e to the first power equals e, so that's just 1. Right? E to what power equals e? E to what power equals e? E to the first power equals e, so that's 1. And then we bring the 2 down in front, and then that's it for that. Okay, now we're going to go in reverse here and put these back together. So that normally we would write the coefficient in front, just convention, that's what we do. Here, so I want to take the exponent down, I'm going to do this in one step, so I'm going to move that in there, and then we're going to divide, so we're going to be, or subtracting, so we're going to divide. So that would be the natural log of x over x plus 1 cubed. I did that 2 steps at the same time there, sort of. Okay, so here we have a few things going on. Take that in there. Those are both subtracted, so we're going to have the natural log, and then here we're going to have x squared, and then down here we're going to have x plus 1 times x minus 1. Now, there's not really an advantage to multiplying that out as a difference of 2 squares. It's probably better just to leave it that way. Okay. So, back before calculators, slide rules were something else that people used. People had books on their desk where they could look up. These logarithms can be calculated by hand. I never learned how to do that because we had calculators when I was growing up, believe it or not. But anyway, so if you had a job where you had some math, you did have a book on your desk where you could look up these numbers, but some of the numbers you probably just memorized because you used them so often. Like most of us know that pi is 3.1415926, etc. Because we use that a lot. So what they would have done was they would have memorized some of the lower natural logs so that they could break these things down. So what you would want to do is break that down into these so that you could use those numbers that you might have had memorized. So this would be the natural log of 3 times 2 squared. And so then you would separate that into the natural log of 3 plus the natural log of 2 squared, and then you would bring the 2 out for that. Okay, so then you would have memorized that the natural log of 3 is 1.099, and here we're going to have 2 times, that's 0.693. Now you can see how a lot of these jobs would have been very tedious because you would have been doing a lot of arithmetic. So a lot of time was spent figuring things out and doing simple calculations like this before calculators. Alright, so here 2 times this would be 1.386. That's 6, 18, carry the 1, 12, 13. So then you would just add those together, you can see that it'd be very easy to make a mistake with all these calculations. Okay, that's right there. Alright, so this one, that's going to be 3 cubed, so that's going to be 3 times, I do that sometimes, start to write an h, 3 natural log of 3, bringing the exponent out in front. So that's going to be 1.099 times 3, so that's going to be 27, that's going to be 29, that's going to be 0, so bring that down, and then 3. Alright. Now, if you think about what we have here, that's 1/2, so we could bring that down in front, so that would be 1/2. And then we have 18, so that's going to be 2 times 3 squared. So that's going to be 1/2, and then we have the natural log of 2 plus, and then we bring that down, 2 natural log of 3. Okay, so 2 times, yeah, we don't have that yet. We did 2 times the natural log of 2, and we did 3 times the natural log. So 1.099 times 2 is 0.1. Alright. So that is right here, 2.198. And this was 0.693. So we need to add those together. Can we add those? I guess I should stack this over here. It's going to be 1, carry the 1, 9, carry the 1, 8, 2. So we have half of that. So that's going to lead us to some long division over here. 2.891 divided by 2. It's going to be 1. It'll be gone. 4. That'll be gone. 9. 4. 1, 1. It's going to be 5. 10, 1, 5, repeating. So in calculus we're supposed to go to 3 decimal places, so that would be 1.446, and that does matter. You do have to round off properly to the 3rd decimal place. So that is our review of pre-calc, pretty much. So let's start doing some calculus. Well, before we do that, why am I talking about E here? Oh, because it's right here. So if we do that same thing with the graph that we did on the front, so we have 1 here, and then we have E over here. So this would be something like that. And there it goes. So E is defined as the number that where the integral of this equals 1. The natural log of E equals 1. And so that's how E is defined this way. The way that most of you were introduced to E was compound interest, and taking the limit as the compounding period goes to infinity, and you call that continuously, compounded continuously. And you had the interest formula, which was 1 plus 1 over x to the x power. That was actually over 1 over I can't remember r, and then n times r up here, the compounding period and the years time, and that's E. So that's how you were introduced to it, but it also fits this situation over here. Okay, again, that's not really important to what you have to do. Alright, so where's the calculus? So everything we've done so far is just review, getting us to this point right here. This is today's lesson, these two things. Alright, so the derivative of the natural log is 1 over x. So you just have to memorize that. All of you can memorize that right now. No matter what you did first semester, no matter what grade you got, you all are equal when it comes to this concept. Well, this part, not this part, because the more you practiced first semester, the easier this will be. But this part, you're all equal. So all of you need to memorize the derivative of the natural log is 1 over x, as long as x is greater than 0. Now over here, we're going to use the chain rule. So the derivative of the natural log of u is 1 over u times du, times the derivative of whatever's inside there. So now we're just going to practice that a couple times. This is the u situation. U is 1/3 of x. So if we take, maybe you need to rewrite on that, 1/3 of x. Another way to look at that. So 1 over u would be this times the derivative of that. That's the du dx. So the derivative of that is 1/3. And if you multiply 1/3 times this, so 1 times 1 is 1. If you multiply 3 times this, these are going to cancel out. So that just turns out to be 1 over x. Okay, now here, hopefully you remember what the heart stands for. It stands for rewrite. Rewrite is our friend. It helps us out a lot. So what we want to do here is think about this as the sine of x to the 1/2 power. Okay, so what we can do is, one of the reasons why we learned those properties of logarithms was because now we can use that. So we can bring that 1/2 out in front of the natural log, and we have this. Okay, so now we're going to take the derivative of that. That's just a constant, so that's just going to be 1/2. Now, the derivative of the natural log is 1 over u times, and you can pause this, it'd be a good idea, just like last semester, pause it and try to do it yourself following the steps there, times the derivative of u, times the derivative of this, which we wrote it to this. So the derivative of sine is cosine. Hopefully you remember your trig derivatives. If not, you better review those real quick. And so that's going to be 1/2 of cosine over sine, and hopefully you know that cosine over sine is cotangent. Okay? Alright. So pause. Derivative of a natural log. The derivative of a natural log is 1 over u times, so this should be pretty nice, these first couple examples, pretty nice, times the derivative of u, so that's going to be 3x squared. So that's going to be 3x squared. Do not try to cancel out those x's. This is together. You can't cancel out terms. Stuff that's separated by pluses and minuses, those are terms. Okay, you can only factor out factors. These are factors. 3 times x squared. Those are factors. These are terms. Okay, those are factors. These are terms. You can't cancel out terms. Now if I could factor out, if there was an x here, I could factor out an x, and then I could cancel that x out with that x, because then they would both be factors. Factors versus terms. Okay, so that's the answer there. Alright, now here, we should recognize recognition. Okay, this is the alternate form of the limit definition of the derivative. So we recognize that when we see it. We say, oh yeah, okay. So this, the alternate form, that's the function right there. So that's f of x. So that's what we want. That's the main thing when you see this, is to identify what is the function that we have there. Alright? So that's our function. Now the whole point of this is they're not going to ask you that long process of finding the limit definition of the derivative where we have to do the steps. They're just going to ask you to recognize it. So you recognize it, you spot the function, and then you take the derivative. You're not actually going to do anything with limits. You're going to take the derivative of that. So that's what we just learned. You should be able to pause this, and that is 1 over u times du, but that's just 1. So it's just that. And then you're evaluating it. This is the c. That's what the number you're evaluating it at. And you can see if we plug 1 in there, we get 1 plus 2 is 3. So we're evaluating the derivative at 1. Alright, so that is 1 over 1 plus 2. So the answer is 1/3. Alright, so let's wrap up this page. And when you see this, hopefully you realize if you try to use that rule, 1 over u, so we do 1 over this, and then we multiply by the derivative of this, we're going to have to use the quotient rule, and the chain rule, and the chain rule. That's going to be pretty messy. Yuck. So that's where we see the heart over here again, rewrite. We should rewrite this using the properties of logarithms. That'll make it a little bit nicer. And I'm going to kind of do 2 steps at once here. So it would be the natural log of this minus the natural log of this, but we have that exponent, that 1/2. So I'm going to bring that down, 1/2 natural log of x squared plus 1 minus, and here we'd have the natural log of this, but there's an exponent also, so I can bring that out to, so I'm trying to save ourselves from not having to write a bunch of steps out. So I hope you all see that as us breaking down that, and that's something you did definitely last year, hopefully the last 2 years maybe, unless you skipped. But if you skipped, it was because you were good at that stuff anyway, so you should be all right. Okay, now we're taking the derivative of that. So the derivative of that is going to be, that's just a constant. It's not the product rule. We don't need the product rule. That's just a constant. So the derivative of the natural log, this is what, over and over again, try to memorize this. You should be memorizing it right now. It's 1 over the function times the derivative of the function, which is 2x, minus, and the same thing here. Now, really what you could do is you could do 1 over this, and when you realize times the derivative of that, that would be times 9. You could just write that up here if you kind of want to save yourself a little bit there. This 2 is going to cancel out with that 2, and so we're left with x over x squared plus 1 minus 18 over 9x minus 4. Do not try to cancel out the 9 with the 18. You can't do that. It's not correct. Okay? Alright. Last page. Logarithmic differentiation. Okay, so this is a little bit tricky, and it's a lot of steps, so that I don't think they will ask something like this on the AP exam. I used to put it on a test, but I probably won't this year unless we're back in person. Okay, so we want to find the derivative of this. Well, if you look at that, that's pretty nasty. That's going to be a quotient rule, and then inside the quotient rule I have a product rule with a chain rule and a chain rule. So really unpleasant. When you look at that, you should be like, yeah, I don't want to do the quotient rule on that. And so there's probably a way around that. And the way around it is to change this to a y and take the natural log of both sides. So we're going to have the natural log of y, and then we're going to have the natural log of this side. And if we have the natural log of this side, we're going to use the properties of logarithms, if we had the natural log of all this, to break that up into parts. Okay, so if we think about that, that would be the natural log, and that 2 I could bring out in front, and that's going to be x plus 1, plus the natural log of this. And you can't take that exponent out because it's not on the whole thing. It's just on this term. And so we can't do that. And then we have a minus here, and that's to the 1/2 power, so we can take that 1/2 out. And also we can't take this exponent out because it's just to the term. Okay, so we did that because using the quotient rule to take the derivative of this would have been pretty unpleasant. And some of you might be thinking, well, that's unpleasant. Well, it's not that bad. So if we take the derivative here, now we have to use implicit differentiation. So we're going to take the derivative of this. That's going to be 1 over y dy dx. We took the derivative with respect to y on that side. Now here, that's going to be 1 over this times, okay, so 2 times 1 over this times the derivative of this. The derivative of this is just 1 though, and remember we said we could put that in the numerator, and that's times 2, so I'm just going to do that. And then plus, and the derivative of the natural log, this is the pretty much today's lesson, that's it, is 1 over this. Notice how I didn't put the 1, times the derivative of this, which would just be 4x. Okay? And finally, down here, we have minus, we have 1/2 there. Let's see what happens with that. So this is going to be 1 over this times the derivative of that. The derivative of that's 2x. So the 2x, the 2 is going to cancel out, so it's just going to be x. You could write that over here on the side if you need to. So it's 1 over this times 2x, and then that was times 1/2. So that 1/2 canceled out the 2. So that, we're almost done. Now we're going to multiply both sides by y, or multiply the whole thing times y. So this is going to cancel out here. We're just going to get dy dx. And then we would have y times this side over here. Now y is up there, so that would be, what am I doing? I'm writing down y. This is y. And that y is being multiplied by this. And it may look intimidating, it may look scary, but if you go one step at a time, it's really not that bad. And so how would you know to do that? You would know to do that because the quotient rule on that's a nightmare. So that should be your indicator there. Okay, wrapping up these notes, first notes of 2021 is a question from 2011. So this is a number 2, so that means it would have been on the calculator part of the test. So as you read the question, you want to take some notes on it. How it cools, differentiable function, h 0 to 10, minutes, Celsius. Okay, so use the data in the table to approximate the rate. Approximate the rate at which a temperature of the T is changing at the time 3.5. So this is on almost every test, and it should be an easy point for us. So they're asking us to find the temperature, the rate that the temperature is changing at 3.5, which is in between 2 and 3. So they're asking us for a rate in between two values of the table. So what we're going to do is use a secant line to approximate that. So we're just going to calculate the slope. 3.5 would be in between here. So that's going to be 52 minus 60 over 5 minus 2, and showing the computations, that's right here. So on the real test, that's what we would put. We do not want to do those steps because so many students make a mistake. Like a lot of students will put 8 over 3. And you say, well, I wouldn't do that. Hundreds, thousands of students do that. And they're not dumb, it's just careless. It's easy to make little mistakes like that when we do things. So leave it like that. Now, over on the side here, I'm going to put this So negative 8/3 degrees Celsius per minute. That's the rate. But do not do that. Do not risk messing that up. Okay, so the next thing is using the correct units. So that's important. That should stand out to you. You've got to make sure that you have units in your answer. Okay, so explain the meaning of this in the context of this problem, and then use a trapezoidal sum with 4 subintervals to estimate that value. Okay, so the first thing you want to look at here is when you have an integral and you have 1 over b minus a, that's the average value. So that's the average value in the what we're talking about here is temperature. So that's the average temperature in degrees Celsius from 0 to 10 minutes. So that's the first part where they asked you to describe what that means. Now they want us to use a trapezoidal sum to approximate this. Okay, so I'm going to put that up here. Actually, this gives us more space. So a trapezoidal sum, first of all, what happens to some students is they just do the trapezoidal sum and they leave off that part. So that's the first thing, is don't lose track of that 1/10. The trapezoidal sum is just for this piece over here. Okay, so the trapezoid is going to be, we're going to have 1/2 because of the trapezoid formula. Now the problem here is that all these gaps are different. This is 2, this is 3, this is 4, this is 1. So I can't just factor out the width. If this was 2, 4, 6, 8, I could factor out a 2 because they would all have an equal width of 2. So this is a great review also. We're reviewing a couple different things here. This is from Chapter 2. What we're doing now, this is from Chapter 4. This is from 4.6. So this is a great review, and that will happen as we're moving forward here. We're going to review a lot of things to strengthen our skills here. All right, so now the trapezoidal situation here, we factored out that 1/2, and now inside here we're going to have the 2 bases. So here we're going to have, so if we take the first 2 bases, that's going to be 66 plus 60. And then the gap here is 2, so that's going to be times 2. Then our next 2 bases would be 60 and 52. And this is where if they were equal, all of these gaps, then we could have just done 166, and then we could have multiplied 2 times 60, 52, and 54. But it's not equal, so we have to do each one separately. So here, this gap is 3 between here. So that was 2, that's 3. Then the next one is 52 and 44, and that gap is 4. And then the last one is 44 and 43, and that gap is 1. Okay. And that would be our answer for this, and we would leave it like that. And we might want to, the average value is the average temperature, so we should put degrees Celsius in there to have the units on it, and we should not do that arithmetic. It takes up time and will probably possibly mess something up. Now you do have the calculator, you could type it in, but again, you're wasting time typing that in the calculator because we don't need to. We could just express the answer like that. Okay, now evaluate this using the correct units, explain what it means. So what we can do here is we're taking the integral of a derivative. So that's just going to give us the function. So that's going to be h of t from 0 to 10. Now this is pretty easy once you realize to make that switch. So now you just plug that in. So that's h of 10 minus h of 0. So h of 10 from the chart there is 43, and h of 0 is 66 degrees Celsius. You don't have to do that arithmetic, and you shouldn't, because it wastes time and you risk making a mistake. And then it said, using the correct units, explain that. So the temperature changed negative 23 degrees Celsius from 0 to 10 minutes. So that's your explanation for that. Okay, now this is why do we have this question right here? And actually it's because this is an exponential, but we're not actually going to worry about that because the calculator would be typing that in the calculator. So that's not a big deal. But still a good review question, all this stuff. So at 0, the biscuits have a temperature of 100 degrees. So we could say B of 0 equals 100 or 0, 100. So we want to try and jot down some stuff that might help us with the question. Okay. The temperature of the biscuits is modeled by a differentiable function b, and we know that the derivative of b is equal to this. Using the given models at time equals 10, how much cooler are the biscuits than the tea? Alright, so we need to calculate the temperature of the biscuits. So the biscuits, if we integrate a rate, we get an amount. So if we integrate the rate, this is the rate of change of the temperature of the biscuits. Because that B is the temperature of the biscuits, so the derivative is the rate. So if we integrate that, we will get B of t from 0 to 10, which would be B of 10 minus B of 0. Okay? So B of 10 is going to be, so we can evaluate this integral. So that's going to be, you're going to type this in your calculator, the integral, and then you're going to type this in, and then comma, I would use x though, comma, x, comma, 0, comma, 10. And then the calculator will tell you that that's negative 65.817 ... You can store that in A, or wherever. And then that's going to equal B of 10 minus B of 0, which is 100. They told us that right there. So if we add 100 to both sides here, then we're going to get B of 10 equals 34.183. Okay, so we need H of 10 minus B of 10. So H of 10 is 43 minus 34.183. So the biscuits are 8.817 degrees Celsius cooler than the tea at t equals 10 minutes. Alright, and that's our first lesson of 2021, although I hope most of you are doing it over the break. Have a good day.